Alright, hello students, welcome to another video lecture for ComSci 137 Data Communications and Networking. So we're now into chapter 4, which is digital transmission, and this will be the focus of this chapter. From the objectives, we have the following. First, you should be able to differentiate data element from signal element, differentiate data rate from signal rate, explain the relationship among data rate, signal rate, and effective bandwidth, describe the desirable properties of encoding techniques, and next is describe how bits are encoded using different techniques for digital transmission, and lastly describe how analog data are encoded using different techniques for digital transmission. Okay, so it's all about digital transmission. Okay, for digital data to digital signal conversion techniques, we actually have three approaches. We have line coding, block coding, and scrambling. But before we proceed with the different encoding techniques, let us define or recall some terms first. Starting with line coding. So for some definitions, we assume or we know that digital data is assumed to be stored in the memory as sequence of bits. So we have digital systems, we have computers, then data is stored as bits. And if you want to send digital data across the link, like this one, we need some form of encoder to convert the digital data to digital signal. And notice that the representation of digital signal here is as a square wave. Then at the receiver end, we have a decoder that will sample the digital signal and then convert that signal to digital data that can now be used by the computer in the receiver. So this is our sort of an outline for this chapter. We're going to discuss techniques how this digital data is converted to this digital signal. Okay, let's have some definition of terms, characteristics. Okay, so first we define what we call a data element. A data element is the smallest entity that can represent a piece of information. We know that as the bit, ones and zeros. Then we differentiate that from signal element. A signal element is the shortest unit, time-wise, of digital signal. Okay? So we have data element, a signal element. We can define a variable R, which is the number of data elements carried by each signal element. So normally, if you have one data element, you have one signal element, therefore R equals 1. So if you have 1:1 mapping, but it's also possible actually to represent multiple data elements for just a single signal element and the other way around. So let's take a look at the different R values. Again, R is the number of data elements carried by each signal element. So in this example, we have, so these are the data elements 1, 0, and 1, and then this is the signal element, which is the square wave. So one data element for one signal element, which is this value 0, 1 is this value, and r equals 1. Here we have one data element 0 is represented by these two signal elements from negative to positive. So we have 1 over 2, so we have r equals 1/2. In this example here, we have two data elements 0, 1, and this is represented by a single signal, a single negative signal. Therefore, using the formula for r equals 2. And the same with this one. So we have four data elements 1, 1, 0, 1 represented by these three values, three signal elements. Therefore, we have r equals 4 over 3. So let's stick to this definition in the meantime. Now, also, we can look at the data rate. Data rate is also known as the bit rate, which is the number of bits sent in 1 second, and the unit is bits per second. Then we define signal rate, also known as pulse rate, modulation rate, or baud rate. This is the number of signal elements sent in 1 second, and the unit of measure is baud, B-A-U-D. So given these characteristics or these definitions, how do we use this to create the encoding techniques that we're going to use, so to convert digital data to digital signal? Our ultimate goal actually is to increase the data rate, meaning to increase the number of bits sent in 1 second, thereby increasing the speed while decreasing the signal rate. When we decrease the signal rate, essentially what we're doing is we're lessening the bandwidth requirement for the signal. Right? So recall our definition of bandwidth, but we're going to look back to review them here later. So given these definitions, we can have a relationship between, we can define a relationship between the data rate and the number of signal elements. So this is actually the formula S, number of signal elements, is equal to this C times C, which is a case factor, which is some constant C. N is the data rate, and R is the ratio of data element per signal element. So we're going to see this parameter later, because when we look at the different encoding techniques, we're going to look at this value. Now let's define the effective bandwidth. So recall in the previous chapter, wherein if we have a non-periodic digital signal, the bandwidth is infinite. Okay? And we call that bandwidth as absolute bandwidth. Now here, when we discuss encoding techniques, it is actually the baud rate, as shown here, the baud rate, number of signal elements sent in 1 second, which determines the required bandwidth. So we can say that the bandwidth is proportional to baud rate, meaning if we have a high baud rate, then it will require a higher bandwidth. And given this direct proportionality, we have here S, so we can actually define the minimum bandwidth as the same as this one here, the signal rate, C times N times 1 over R, because it's essentially equal to the signaling rate. And by manipulating this equation, we can get N max, which is equal to 1 over C times B times R, which is actually BR over C. So again, N is the data rate. So essentially, the higher the bandwidth, the higher the data rate. Okay, let's talk about baseline wandering. So these are just some important terms that we're going to use when we describe the different encoding techniques. So the first one, the next term that we need to define is called baseline wandering. So when we give an example here, baseline wandering. So the receiver calculates a running average of the received power signal, and that running average is used as a baseline. So it's actually a threshold, and the incoming signal is evaluated against this baseline to determine whether the signal represents 1 or 0. So let's go back to this figure here. So at the receiver end, these signals here will be sampled, and then the receiver will define a threshold such that anything above this threshold will be considered, let's say, 1, or anything below this threshold will be considered 0. Now, the problem with the main issue about baseline wandering is if you have a long sequence of zeros or a long sequence of ones, it's possible to cause a drift in the baseline, meaning the actual threshold will be wrong, because if you are just receiving a continuous flat signal or zero signal, or you are just receiving a long sequence of ones, so the receiver end will not be able to properly determine the running average of the signal to generate the correct threshold. So there will be misinterpretation of the bits. So it is important that the line coding scheme should prevent this baseline wandering. So as much as possible, prevent sending long sequence of zeros or long sequence of ones. We'll discuss techniques how to handle this later. Then we also have DC components. So DC components are direct current components. So when we talk about the bandwidth of a signal, it's possible that the signal will have frequency components that are very low or near the zero frequency. So remember our plot, right? So let's say this is the plot of our frequency component, right? And this component here, this is zero frequency, right? is called DC components. Now the problem with encoding schemes that have DC components is that there are some transmission media or systems that cannot pass very low frequencies. An example of that is the plain old telephone system or POTS, which cannot pass frequencies below 200 Hz. So if your encoding will have a frequency component very low, like or zero, or called the DC component, then it will not be able to pass through the medium. So ideally, no DC component should be present in the encoding scheme. Then the next one is synchronization. Okay. So timing information is should be in the signal itself. Okay, because when the timing are not synchronized between the sender and the receiver, it may be the case that the receiver will be sampling too fast than the sender sending in a different time. So here's an example of a lack of synchronization. So on the sender end, this is the signal generated. So this is the timing, the interval or the bit duration within this interval. This is the time that the sender emits the signal that represents the bits. But on the receiver end, for example, if the receiver end samples the signal at half the time of the sender, then there will be misinterpretation, because the receiver is sampling the signals from the medium or on the medium at a different time than in the sender. So at the receiver end, this will be the bits that it will process, while originally this is supposed to be the bit stream to be processed. Okay, so the ideal is that the timing should be embedded in the signal itself. Other characteristics that are to be considered when considering encoding techniques. The signal should have a built-in error detection. So it's possible that, since we are using digital signals, recall our discussion about transmission impairments. So it's possible that, let's say, 0 will become 1. So the encoding scheme should have a built-in error detection. In relation to that, it should also be immune or somehow immune to noise, which is a form of transmission impairment discussed in the previous chapter. Of course, complexity. So the schemes should be simple, because too much complexity affects performance and can actually reduce the reliability of the system. Okay. So, given these definitions and some ideal characteristics of encoding schemes, let's now look at the different line encoding schemes. So, it's roughly classified into 5 classifications. So, the first one is unipolar. In the unipolar line encoding scheme, all signal levels are above or below the time axis. So we actually have a unipolar NRZ. So that's one encoding scheme under this category. The second one is polar, wherein the signal levels are on both sides of the time axis. The time axis is the x-axis. So we have polar NRZ, polar RZ. We have biphase, which have Manchester and differential Manchester. Then we have bipolar, wherein you have three levels: positive, negative, and zero. And one signal level alternates between positive and negative. So we have two examples, two encoding techniques under this category. We have AMI and pseudo-ternary. For multi-level, we increase the number of bits per bond. So we try to increase the number of signal elements or data elements per signal element. So we have 2B1Q, 2B/1Q, 8B/60, and 4D-PAM5. And the last category is called multi-transition, and the example or the encoding scheme here is MLP3. So let's discuss each of these line coding scheme, and let's start with the unipolar non-return to zero. So when you say unipolar, it's above or below the time axis. So this is the somehow simplest encoding scheme. So we have the y-axis for the voltage level, and then we have the zero voltage here, and this is the time axis. So non-return to zero, so we have 1 to represent high voltage here to represent 1, then zero voltage to represent 0. So very straightforward. The main disadvantage of this encoding scheme is that it requires high power requirement, shown here. So this is not a good coding scheme because of this high power requirement. So the next is polar NRZ. Okay, so NRZ-L or NRZ level, here the level of the voltage determines the value of the beat. So for example here, this is an NRZ-L. The level here is positive, this is positive, this is negative. So 0 is positive, 1 is negative, 0 positive, 0 positive, 1 is negative. So it is the voltage level that determines the value of the beat. For the NRZ-I invert, the change or the lack of change in the level of the voltage determines the value of the beat. Meaning, if there is no change in the voltage level, then the value is 0. So let's take a look at an example here. So assuming that somewhere here, this is the voltage level, so no change, so this will be 0. Now if this is 1, there should be a change from positive to negative, so that is 1. No change, 0, no change, 0, 1. There should be a change from negative to positive, and you get the idea of NRZ-I. And these are the characteristics of this encoding scheme. R equals 1, meaning obviously you have one data element for one signal element, so R equals 1, and we have the bit rate here, or average signaling rate, which is n over 2. So remember, n is the bit rate. Okay, so half of the bit rate is the signaling rate average, and this is the bandwidth for the signaling. So you will notice that there are some zero components in the bandwidth here for polar NRZ. Okay. So the next one is polar RZ. So the NRZ, it simply ignores the zero voltage level, but in polar RZ we have we consider the zero voltage level. So here in the polar RZ we have a mid-bit transition. So remember that this is the bit duration. This is the duration of a bit. So this is the bit duration. There is a mid-bit transition here, and the advantage of having a mid-bit transition is that it solves the synchronization problem discussed earlier. It is more, though it's more complex, more bandwidth requirement, okay, and the advantage is there is no DC component, so the bandwidth is concentrated here, and we have one data element for two signal elements. So let's take an example. So we have 0 here. So essentially this is the 0 level, but there is a mid-bit transition. So this is negative, this is positive, this is 0. So the mid-bit transition happened here. So from negative to 0, then 0 to positive. To represent 1, we have from positive, which actually positive is positive, then the mid-bit transition. Then we have 0 here, so we start with switch to the bottom, then mid-bit transition. Okay. So two signaling elements per one bit, and this is also 0, so this one is negative, and then we have a mid-bit transition going back to 0. That's why it's called return to 0, etc., etc. And of course you get the idea of this polar RZ. So the next one is the Manchester differential Manchester encoding. It also has a mid-bit transition for synchronization. However, it requires twice the bandwidth of NRZ. So here 0 is represented as the transition from high to low, and 1 is represented as transition from low to high. So let's say for Manchester, so we have again, this is 0, this is 1, transition from high to low, and then 0 again, so low to high, then 0 again, so low to high. So in terms of R, we have one data element per two signaling elements, so we have R equals 1 over 2. And the baud rate is equal to the bit rate, and this is the bandwidth, so there is no, again, no DC component. For the differential Manchester, So 0 is represented, this is similar to the NRZI. So no inversion, next bit is 1. If there is an inversion, next bit is 0. So here we have no inversion, so the next bit is 1. And then we have an inversion here, so the next bit is 0. Okay, so this is very similar to this one here, okay, NRZI. So the previous the change in the level determines the value, whether it is 1 or 0. Okay, so that's Manchester and differential Manchester, and it's the bandwidth. So you can compare the bandwidth here. Okay. So it's 1, here 0.5. Then the next one is AMI and sync-ternary. AMI means alternate mark inversion, wherein the neutral or zero voltage is 0 and ones it can be represented by positive or negative voltage. So let's take a look at an example. So 0, we have voltage 0. 1, so assuming this is the first, so we start with positive, then 0 also. Now we have a 1 here. We have to check the previous value of 1, the previous signal level used for 1, which is positive. Therefore, for this one here, we're going to use negative, and then we go back to 0 level. If we have a 1 here, then this will be the signal for this value, and we only have one data element per signal element, so we have R equals 1, and the bandwidth, so half of the bit rate, baud rate, and this is the appearance of the bandwidth. Okay. So for pseudo-ternary, it's just the opposite. So 1 is represented by 0 voltage, and 0 is represented by alternating zeros and alternating positive voltages, positive and negative voltages. Shown here. Okay, so there. Some of the characteristics of the AMI and pseudo-ternary. Now let's move on to multi-level schemes. Now in multi-level schemes, the idea is to encode a pattern of M data elements into a pattern of N signal elements. So there's a kind of mapping, encoding scheme. 2 to the M data patterns, and we have L signal patterns. Remember, L is the signal level. Okay. So if 2 to the M equals L to the N, then each data pattern is encoded in one signal pattern. If 2 to the M is less than L to the N, then data elements occupy a subset of the signal patterns. So this is the notation. The notation is M, number of data elements, B, and N, by number of signal elements, L. So this pattern of M data elements is encoded in a pattern of N signal elements in which 2 to the M is less than or equal to L to the N. So let's take a look at an example of a multi-level scheme called 2B1Q. Okay, so it means 2 binary, 1 quaternary, which is 4 signal levels. So this is used in DSL. Okay. So we have here's an example. If the previous level, we have a lookup table actually. So the next bits, if the next bits are this, then the signal level will be these values depending on the previous level. So let's take a look at an example. So we have 0, 0. Okay. Let's consider 1, 1. So 1, 1. So the next bit is 1, 1. And the previous level is positive. Therefore, the signal level that we're going to use is negative. If the next bits are 0, 1 and the previous level is negative, then the next level, the signal is negative 3. If we have 1, 0 and then the previous level is negative, then we have +1 for 1 and 0. So this is an example of a multi-level scheme. So our voltage levels are 1, 3, -1, -3. So in this multi-level scheme, our R is one data element per 2 signal elements, and the bandwidth requirement is N/4 bitrate, and this is the bandwidth, so it has a very small bandwidth requirement. However, there is a DC component here. Then we also have 8B60, so 8 binary and 6 ternary, 3 signal levels. Remember that L here is the number of signal levels. So this is used in fast Ethernet, 100 base 40 twisted pair, and the bandwidth is 6N/8. So here's an example for this bit pattern. We have 1, 2, 3, 4, 5, 6 signal elements to represent this, and we have 3 signal levels, negative, 0, and positive. For this bit pattern, Okay? So we have this combination. So these are, again, what happens is at the receiver end, within this period, okay, if the receiver receive this signal pattern, it will interpret it as these bits. Okay, so that's that. Then we also have 4D PAM5. This is a 4-dimensional 5-level pulse amplitude modulation, and this is used in gigabit LAN. So this one is used in fast Ethernet 100 Mbps, and this one is in gigabit Ethernet. It's used as 4 wires. Here it's usually just 2 wires. So to accomplish this, there's a kind of assignment per wire. So you have this bit pattern, and they will be assigned to different wires. So to be able to achieve a 1 Gbps bit rate. It's 4-dimensional because we have 4 wires and 1, 2, 3, 4, 5-level pulse. So it's including the 0 here. Okay, so the last one is multi-line transmission, which is an example of which is MLT3. So we have a state transition diagram to determine the possible values. So this is a more advanced encoding scheme. So to summarize the different line coding schemes, so we have unipolar, it's the bandwidth, average bandwidth. Okay. So this is actually S, right? So this is the S in the figures. Okay. And yeah, it's just the summary. So you can compare the different encoding schemes. So we'll continue on the next video with the block coding and scrambling techniques.